This is lesson 4.7, using L'Hopital's rule for determining limits of indeterminate forms. Before we get to the rule and what it is, let's review some prior knowledge here. So we're going to do a quick review of what an indeterminate form is. So right here, I have a definition for you all. An indeterminate form is a value that has no clear answer. And it says some examples are listed for you below. Now, if you remember from chapter 1, we talked about this one here and this one here. These other ones are some new examples for you. And not all these examples in the box, that is not all the indeterminate forms out there. There's many, many more. I just decided to give you some 5 most common ones, but there's lots of ones out there. Now, these two that we've already talked about, those are the most common ones. So you have 0 over 0. Remember, that could be 1. That could also be 0. That's why it's indeterminate. We don't know. Same thing with infinity over infinity. Infinity divided by infinity, that could be 1. It could also be infinity. We don't know. But then you also have these other weird examples, okay? So let me talk about this one, for example. 1 to the infinity. Two kind of conflicting math rules going on here. 1 to any power is always going to be 1. 1 squared is 1. 1 to the third is 1. 1 to the infinity should also be 1. However, any number to the infinity power is infinity. So which is it? Is it 1 or is it infinity? We don't know. That's why it's indeterminate. Okay, so lots of different types of indeterminate forms. Sometimes you run into these when you're trying to take a limit. That does not mean give up. That does not mean the limit doesn't exist. It just means you have 2 options for trying to proceed. You could either use algebraic manipulation on the limit. So remember, we talked about that in chapter 1. That's when you try and rearrange, simplify, do whatever you need to do to try and get the limit to exist. Or you could use L'Hopital's rule. And yes, it has an S in it like hospital. Okay. Now, algebraic manipulation. 1, it doesn't always work. 2, sometimes it's really, really hard to do. So that's why L'Hopital's rule is our friend. It's a nice little shortcut. But before we get into it, let's just do another quick review of algebraic manipulation, all right? So here you go. You have 2 limits here in this box. One's an infinite limit, one is a finite limit. So we have the limit as x approaches 4 of x squared minus 16 over x minus 4. And then we've got this infinite one over here, the limit as x approaches infinity of 4x squared minus 5x over 1 minus 3x squared. All right, so with indeterminate forms, remember they pop up whenever we try and plug in the limit value directly into the equation. So when I evaluate this limit directly, I am going to literally just rewrite it. And every time I see an x, I'm going to replace it with that 4. So this would become 4 squared minus 16 over 4 minus 4. And when I simplify and do the math on this, 4 squared, well, I know that's 16 minus 16 on top. And on the bottom, I'm going to have 4 minus 4. Hopefully you see where this is going. 16 minus 16, 0. 4 minus 4, 0. So right there, there's my indeterminate form. That does not mean stop. It just means I'm going to have to do something different to try and get this limit. All right, let's hop over to the other one. Even though it's infinity, yeah, you can still evaluate this limit. All you're going to do is you're going to go through, and every time you see an x, here, here, and here, you're going to replace it with infinity. So we have 4 times infinity squared minus 5 times infinity all over 1 minus 3 times infinity squared. Okay, go ahead and solve it, clean it up. 4 times infinity squared, well, that's just infinity. Minus 5 times infinity, that's also infinity. And then divided by 1 minus 3 times infinity squared is also infinity. So we end up with this. Now you might be tempted, be very careful, you might be tempted here to say infinity minus infinity on the top, that should be 0. No, it is not. Not in this case. It sometimes is, but not here. Once again, if you remember from chapter 1, we talked about how some infinities are bigger than others. So if you guys look, infinity squared, that should be way, way bigger than regular infinity. And so this infinity is bigger than this one. And so if you have a massive number and you subtract a slightly less massive number, you still have a massive number. So on the top, even though it says infinity minus infinity, this is still infinity. Okay, same thing down here. We have 1 minus a massive number. Okay, if I have 1 minus a really big number, that means I should have negative really big number. So I end up with infinity over negative infinity. This is another one of those indeterminate forms. Okay, so now in both of these, in chapter 1, we talked about, all right, that's fine. Just use algebraic manipulation. Rearrange the equation a little bit. Get it to do what you want it to do. So I'll hop back over here. For this one, the first thing I'm going to do before I try and use algebra is I'm going to rewrite this equation so that it says x squared plus 0x minus 16 over x minus 4. And you might be thinking to yourself, well, why did I do that? It's because I know that this x squared means that it's quadratic. And if I have 3 terms, I know how to factor a 3-term quadratic equation. So I went ahead and put this middle term in there, even though it technically doesn't exist. Okay, now I'm going to go ahead and factor it, try and simplify this, do whatever I can to try and get something to cancel out. So right here on the top, I could rewrite this limit if I go ahead and factor the top. That is going to be x minus 4 times x plus 4. And then, of course, still divided by x minus 4. And if you are not very confident in your factoring abilities, remember, I was looking for 2 numbers that when I multiply them together, I get negative 16. So that's why negative 4 times 4, that is negative 16. I'm also looking for 2 numbers that add up to 0. Negative 4 plus 4 is 0. So these are my 2 factors. And hopefully you guys see that these 2 cancel, and I'm left with the limit as x approaches 4 of x plus 4. Way easier to work with, because now if I just plug in 4, I end up with 8. This limit should be 8. Very good. Now, over here, again, even though there's an infinity, we can still do algebraic manipulation and try and get this to work in our favor here. So how do you do that? Well, anytime I have a number times infinity, I'm going to end up with infinity, and that's bad. I'm trying to get rid of these infinities. So once again, if you remember from chapter 1, we talked about 1 divided by infinity. In fact, any number divided by infinity is 0. So if I can get this to say 4 divided by infinity instead of 4 times infinity, I'm going to be in good shape. So I'm probably going to need to divide. Now here you go. It might be a little weird. The infinity replaced the x. So if I go up to this original equation, I need to divide some x's away. So here's a little trick for you. You're going to pick the x with the biggest degree. In this case, there's 2 of them. It doesn't matter. But x squared is the x with the biggest degree. So what we're going to do is we're going to rewrite our limit, and we're going to go through each term, every single part of this, and we're going to divide out that x with the biggest degree. So I'm going to write 4x squared, but I'm going to go ahead and divide it by x squared. And then I'm going to subtract 5x, but I'm going to divide it by x squared. Then on the bottom, we have 1 divided by x squared minus 3x squared, and I'm going to divide that by x squared. Okay, it looks crazy, but it actually cleans up really, really nice. So let's simplify this a little bit. Okay, 4x squared divided by x squared. Well, that's just 4. Then we have minus 5x over x squared. That is 5 over x. Then all over 1 over x squared stays the same. And then I have 3x squared over x squared. This is going to be just minus 3. Now look, my x's are no longer up next to the numbers. They're now in the denominator of fractions. That's good because I'm going to replace those with infinity, and that's what I wanted. So I'm going to go ahead and do that. 4 minus, this is going to be 5 over infinity, divided by 1 over infinity squared, minus 3. So all I did was replace these x's with infinity. Well, I've got 4 minus 5 over infinity is 0. And then 1 over infinity squared, that's also 0. And when all is said and done, I end up with 4 minus 0, which is 4, over 0 minus 3, which is negative 3. Here is the limit. So once again, we had an indeterminate form. We did some fancy math to it. We got an answer, even though it looked like all hope was lost. Now, the problem you guys are going to run into is either A, sometimes algebraic manipulation doesn't work, or B, sometimes it's just really hard to do, like this. This is kind of a difficult concept. So, this is where L'Hopital's rule comes into place. It's kind of like a shortcut. Now, the one thing I want you to pay very careful attention to is L'Hopital's rule only works if you have a fraction. If you're trying to take the limit of something that looks like a fraction, then you can use L'Hopital's rule. It only works for what we call quotients. So we're going to go ahead and add this to our notes. Only works for quotients, for fractions. Okay, so what the rule says is if you're trying to take the limit as x approaches some number of a function with a numerator and a denominator, and you get 0 over 0, or you get some version of infinity over infinity, then you can use the rule. And the rule says the limit as x approaches some number of this crazy equation is going to be equal to the limit of, and you take the derivative of the top, so f prime of x, and you take the derivative of the bottom. Okay, let's look at how this works. All right, so let's look at example 1. Get the limit as x approaches infinity of 4x squared minus 5x over 1 minus 3x squared. Now, hopefully you guys notice right out the gate that this is actually the problem we just did right here. So we've already done this. So I know when I go to use L'Hopital's rule, I should get 4 over negative 3. It should give me the same answer. Now, when you go to use L'Hopital's rule, the first thing you want to do is check to make sure that you actually do have an indeterminate form by just plugging in the limit value. So we've actually already done this part. We've already plugged in infinity, and we know that this equals infinity over negative infinity. So I already know that that's indeterminate, so I'm just going to go ahead and jump straight into L'Hopital's, but you always want to check that first. So here we go. I know that this is going to equal the limit of the derivative of the top over the derivative of the bottom. So I can go ahead and do that. So I have the limit as x approaches infinity, just like normal, of take the derivative of the top here. There's some power rule going on. You've got 8x minus 5 divided by, take the derivative of the bottom. This 1 is going to turn into a 0. This is going to turn into negative 6x. Okay, now, you might be thinking, now wait a minute, we're still not in good shape. If we try and plug in infinity here and here, we still end up with the same problem. 8 times infinity is infinity. Negative 6 times infinity is negative infinity. This is still indeterminate. So where do we go from here? Do L'Hopital's rule again. So I know that this also needs to equal the limit of, take the derivative of the top, I end up with 8, over, take the derivative of the bottom, I end up with negative 6. So my limit is 8 over negative 6, which I know simplifies to 4 over negative 3, which is exactly what we got before. So L'Hopital's rule still gets you the same answer, and it's a lot easier to do. All right, cool. Let's look at some other examples. Example 2 and example 3. So number 2, it says the limit as x approaches 0 of sine of x over x. Now, this is one I had you guys memorize way back when, and you all should know that this is 1. The limit is 1. But we're going to practice using L'Hopital's rule here. So the first thing I need to do is make sure that I have an indeterminate form, and I'm going to do that by plugging in 0. So I should have sine of 0 over 0. And of course, the sine of 0 is 0. So I end up with 0 over 0. So cool. I have an indeterminate form. I can go ahead and do L'Hopital's rule. So I know that this should equal the limit as x approaches 0. I'm going to take the derivative of the top. I'm going to get cosine of x divided by derivative of the bottom. That's 1. And cosine divided by 1, that's just cosine. So now I'm ready to plug in my 0. Cosine of 0 is 1. So yeah, even though you guys memorized a long time ago that this limit is 1, now you know why it's 1, right? L'Hopital's rule lets us get to that answer. All right, cool. Example 3. We have the limit as x approaches infinity of e to the x divided by x squared. So same deal. First thing I'm going to do is I'm going to check and see if I even have an indeterminate form. So I have e to the infinity over infinity squared. Anything to the infinity power, that's just infinity. Infinity squared, still infinity. So boom, there's my indeterminate form. So let's go ahead and use L'Hopital's rule. So I have the limit as x approaches 0, or sorry, not 0, infinity. Gonna take the derivative of the top. Derivative of e to the x is still just e to the x divided by derivative of the bottom. That's 2x. All right, slight problem. If you were to try and plug in infinity here, you'd get e to the infinity, still infinity, and you'd get 2 times infinity, still infinity. So this is still indeterminate. So remember, just do L'Hopital's one more time, or however many times you need to. So again, derive the top, I still get e to the x. Derive the bottom, I get 2. Okay, now when I plug in infinity, I'm going to get e to the infinity over 2. Well, that's just infinity over 2, which is still just infinity. Okay, now, just because you can do L'Hopital's rule does not guarantee you're going to get a limit that exists. This limit technically does not exist because it approaches infinity. However, we couldn't say that before. Remember, indeterminate means it might approach infinity, it might be approaching 1. I don't know. But because of L'Hopital's rule, now we know for sure this limit approaches infinity. All right, cool. Let's look at the last 2 examples here. Bottom of the page. We have the limit in example 4 as x approaches 0 of x times the natural log of x. Now, wait a minute. Coach Connor already said you cannot do L'Hopital's rule unless you have a quotient. And there is no fraction here. This is x times natural log of x. It's very true. However, I can rewrite this. All right. I can rewrite this as the limit as x approaches 0 of the natural log of x divided by 1 over x. So this might seem weird, but remember, when you divide by a fraction, it's the same as multiplying by the inverse or the reciprocal of that fraction. So if you were to flip this 1 over x over, you would get x over 1, or just x. And then you'd multiply that back up top, and you'd end up right back here. So these two, these two are exactly the same, all right? Even though this looks weird, they're the same. Cool. So now I can go ahead and evaluate this just to make sure I have an indeterminate form. So if I plug in 0, I end up with this. The natural log of 0, that is undefined. There's an error there. That's because it's infinity. And then 1 divided by 0, anything divided by 0 is also infinity. So boom, there's my indeterminate form. That means I can use L'Hopital's rule. All right, so let's go ahead and do that. I know that this needs to equal the limit as x approaches 0 of, I'm going to do L'Hopital's rule on this one. So take the derivative of the top, that is 1 over x, divided by derivative of the bottom. Now, you have options here. This is a quotient, so you can do quotient rule. Low d high minus high d low all over low squared. That's fine. You could also rewrite this as x to the negative first power and then do power rule. Whatever, you'll get to the same answer, and that answer will be 1 or negative 1 over x squared. So I trust your guys' ability to take the derivative of that, so I'm just going to shortcut and move forward. So we end up with this. Now, here we go. Let's clean this up a bit. I can rewrite this. Remember, when I divide by fractions, it's the same as multiplying by their reciprocals. So this is now negative x squared over 1. I just flipped it over. And hopefully you guys see, I got 1's that cancel. I got one of these x's is going to cancel with that x. And I am left with the limit as x approaches 0 of negative x. Well, that's going to be negative 0, which is just 0. So now we know the limit as x approaches 0 of x times the natural log of x, that is just 0. Okay, finally, last example. We have example 5. The limit as x approaches infinity of x to the 1 over x power. So this is another one of those that, yes, even though there's a fraction right there, this is x to the power of something. It is not a quotient. So we're going to have to do some sort of rearranging in order to get this to be something that we can use L'Hopital's rule for. But first things first, let me show you that even in this form, we have an indeterminate form. So if I go ahead and replace these x's with infinity, I end up with infinity to the 1 over infinity power. Well, 1 over infinity, that's 0, so I end up with infinity to the 0 power. This is one of those indeterminate forms from the top of the page. All right, now, this one's weird. I'm going to do some fancy footwork here. This is just to show you that L'Hopital's rule can be used in a lot of different ways. So the first thing I'm actually going to do is I'm going to say, I'm going to let y equal x to the 1 over x. And why would I do this? Because then I can take the natural log of both sides, just like this. And there is a rule for logarithms that says if you have an exponent inside the parentheses, you can take this exponent and bring it out to the front. So this is going to equal 1 over x times the natural log of x. All right? In other words, this is going to equal the natural log of x divided by x. This is now a quotient that I maybe want to work with. Okay, cool. So instead of taking the limit of y directly, so the limit of this, we're going to take the limit of this, which is the natural log of y, and we'll fix that at the end, but just bear with me. So I can now take the limit as x approaches infinity of the natural log of y. And of course, I just found out that that is actually equal to the natural log of x over x. If I were to plug in infinity into this directly, I'd get an indeterminate form. So I'm going to use L'Hopital's rule. And I know that this is the limit as x approaches infinity of derivative of the top is 1 over x. And then derivative of the bottom, that's just 1. So this is, oops, whoa. Sorry about that, guys. Here we go. This is the limit as x approaches infinity of 1 over x divided by 1. That's just 1 over x. I can go ahead and plug in my infinity. And anything divided by infinity is 0. So now I know the limit of the natural log of y is equal to 0. Now, I didn't want this limit, though. I wanted the limit of regular y. So now I'm going to have to do one last little step here to see if I can figure that out. Okay, now, again, another weird logarithm rule. I know that e to the natural log of y power is equal to just y, because e and natural log are inverse operations, so they just cancel each other out. So this is a true statement, which means if I take the limit of this, then it's the same as taking the limit of this, which is what I want to do. I want to take the limit of y because y is equal to my original function. Okay, so let's take the limit of this now. All right, so we've got the limit as x approaches infinity of e to the natural log of y power. And there's a really cool property about e that we've kind of talked about before, but not since chapter 1. If you take the limit of e to some exponent, you're allowed to do this. This is the same as e to the power of the limit. So you're allowed to move the limit right into the exponent. And why does this help us? Because we've actually already found this guy. That's what we did right here. It's 0. So this is equal to e to the 0, which is 1. Okay, so a really weird way to use L'Hopital's rule, but this limit right here gave us an indeterminate form. With some fancy footwork, we were able to turn it into a quotient. We were able to use L'Hopital's rule, and then we were able to plug it all back in at the end and get 1. All right, that's it for this lesson. Good job, everyone.